We're going to continue on our quest to figure out the mathematics of how you make CT images and also determining what parameters we need to set in order to make good CT images. And the first thing we figured out, which was a huge deal, and it's a really cool thing from the projection slice theorem, was that our raw data that we get from the scanner, after we normalize it to the air intensity and take the log, looks like this. It's a function, we call it GL theta. L is the detector direction. Theta, in this case, is the particular angle projection that we're on for this 1D data. And so I'd get a whole set of these for different thetas. What we can do, and we found out through the projection slice theorem, is before we back project this stuff, we don't want to back project GL theta, as we saw, because it gives you blurred images and it gives you a background that's a big sort of snowy haze of signal that shouldn't be there. However, if you convolve GL theta with the inverse Fourier transform of the ramp, right? The ramp function, this is the Rom-Lock filter, it's called. So we're going to convolve this thing first to produce something we call G star L theta. We back project those and we get the true image. So in the noiseless, purely well-sampled case, we would reconstruct the actual object, right, accurately. And we looked at some examples of that. I think we got to here, right, last time, which we looked, this is the Rom-Lock or ramp filter, right, in Fourier space. So this is spatial frequency now on this axis, and this is relative amplitude on the y-axis. So the Rom-Lock is a true ramp that just keeps going up and up and up and up until finally we have to cut it off and say anything at higher spatial frequencies probably isn't sampled by our detector. So let's cut this thing off. And it produces images with very sharp edges and high spatial resolution because you have these high spatial frequencies in your data. However, it can cause noisy images, and so oftentimes what's done is the ramp is modulated, or the coefficients that are way out here are decreased such that they go back down to 0 at the bandwidth of our picture. And that produces a much smoother image and has less noise on it. Here's an example of two images, same object, same data, right? So we're just reconstructing this raw data. So all of the GL thetas that we acquired to make this picture are the same for this picture. All we do here is multiply by that Rom-Lock filter. On the scanner, the commercial scanner, this isn't called the Rom-Lock filter, it's called the bone filter. And it probably is slightly different than the pure Rom-Lock filter, but they won't tell you how it's different because in this line of work, these filters are well-guarded trade secrets. And however, you can see much higher spatial frequency information is in here than in here. This is kind of blurry in the background. This is really modelly and high noise. Also, this one admits these high frequency structures along here. These are these bands here and here, and those are aliasing artifacts, right? That given the high frequencies that we can display and reconstruct on here, those artifacts come through because we can actually see things at this frequency. And they're usually caused by a very sharp edge just missing the edge of a single detector, or transiting two detectors, as you move your angles, and it causes these spray artifacts. When we use as opposed to using the Rom-Lock filter or the pure ramp, we roll it down like that filter I just showed you. It reduces the noise considerably, and it reduces these artifacts because you can't visualize those spatial frequencies after you filter with this thing, right? So it makes the image look smoother, much more well-behaved, right? if you look down in the background, you can see all of this spray artifact. There's nothing back there. This is just, the mathematics says, well, the object could have these, things out here, but they're not actually there. And the background noise here it's much smoother after filtering with the broader filter. So in actually implementing this, the continuous function that you would convolve GL theta with is this blue dashed line. That's the continuous inverse Fourier transform of the ramp function. But to do it on a computer, you need to store the coefficients of this function as numbers and then run that convolution as discrete numbers, right? And so actually these guys, what they really contributed was how to produce these discrete filter kernels to get this job done. So when you sample this thing at this frequency to make a kernel that you're going to convolve GL theta with, it looks like this black line, right? And there's just points here, 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 here. And then as we look at Shep-Logan, you can see the peak goes down. It gets a little bit wider, gets wider still, and very wide with this one. So these are all different convolution kernels that correspond to these different filtering techniques from the Ramlock filter. So let's see what they look like practically. So if my GL theta is our friend, the rectangular function, right? So that's a very simple function. When we convolve with that discrete Ramlock filter, so I'm going to convolve this thing with this is the output. It's considerably different than this, right? So you get these negative side lobes plus these really edge sharpening weighting as we're back projecting through this object, right? Shep-Logan, it looks like this. It gets a little bit wide. This transition zone gets a little wider. Hamming looks like this. The peaks aren't as high right here, and it's a little wider. And again, Blackman, the peaks are even wide, spread even wider. So what could go wrong with this method? So here's an example. I have my measured intensity on my detector. This is the L direction here. This is for one specific theta projection. And these are the values of that projection. I convolve it with, let's say the Ramlock filter. Actually, it's not Ramlock because it doesn't have the positive thing here, right? So I convolve it with some filter and get this that I'm going to back project. So, and then we back project, we get a perfect picture. What happens if for one specific theta, say I have 1,000 different projections, different thetas, right? If one of those thetas, something untoward happens in that a device on the patient or something lets off a electrical pulse or a spark or something like that, or one of the detectors, glitches and has some extra voltage. So in one view, we get these little spikes on our projection, and these are artifactual. They're not actually in the object, right? When you take the convolution of this function with something like the Ramlock filter or something like that, it really enhances these things because they have such high spatial frequencies, right? So a spike like that has very broad spatial frequencies, as we've seen, right? And so the ramp function really enhances this thing when you do this convolution. So these little artifacts become quite big on the G star L theta. And then when we back project, we have one view, one theta that has these big spikes on it, and the image looks like this. It has streaks through there at that particular angle. And so when you see that on your images on your patient, right, oh, I've got some discrete noise It's not really noise. It's actually some discrete artifactual signal that happened, right, at a specific theta. You go back to your sinogram and you can find it, right? And basically you go through here and say, this is wrong. Let's just replace these pixels with an interpolation between their neighbors. So I've got some wrong pixel. I think the pixels around it are correct. So just throw out the wrong pixel, interpolate between these two and put a point there, right? That's a relatively harmless way of like getting rid of nasty points, right? This is done. Almost every CT reconstruction that's done is they go through the raw data and they find nasty points and say that can't be true. And they'll just get rid of that point. Otherwise, you get these nasty streaks, right? So in this case, we have L again in this direction. This is a single theta. Our projection comes down and there's a dip. So a number of detectors, for whatever reason, perhaps in one of those whole units. Remember, we looked at our detectors and they came in those chiclet-sized things. They're like 16 by 32. Maybe that whole panel, the preamp for that thing went down for some reason, and it's giving us an erroneous signal. So here it is, right? So it's exactly like the same error we saw before, except because it doesn't have sharp edges, it's sort of a better behaved artifact, but it still produces this dark signal all the way through the picture, right? And at a specific angle, which is this projection, right? So, and if you go across here, you would see these edges, of that projection. So now, suppose we have a 1% error, right, in our projection. So this is, again, L, our channel number for a specific theta. We look at the data, and we can't even see that there's an obvious error in this data, right? You look at it and go, well, this looks perfectly fine. After you do the convolution, it just reaches up its little head, right? That, oh yeah, that doesn't look right. There's something wrong here. The reason we can see it is this object is so darn simple that these things stand out on the raw data. If it's a complex object, it's going to be really hard to do this, right? So anyway, you've got this thing here, and if it occurs on every theta, so let's say that detector, just a 1 by 1 by 1 millimeter little detector, for whatever reason, had a 1% drop in its from the pre-calibrated voltage that should come out of there because the amplifier's flaky, and it happens on every theta, then the image looks like this, and you get a ring at a specific radius, whatever the radius is of that detector, right? It just squirts back onto the image. These rings are when you take images on a clinical scanner and you lower and lower the dose, when you go towards the center, you can start seeing just faint rings, right? Because they're super hard to get rid of. Like the calibration, right, of the pre-calibration of those preamps, even though you did it this morning, might have faded by 5 o'clock. And so that very small percentage change gives you this ring artifact. And you can usually, if you look carefully enough, see them, right? Now, if the signal's really big and stuff, the ring can be drowned out by the other signal. But here the signal's totally uniform, so it's sort of the worst case scenario for seeing that. Okay, so in the book, okay, this is equation 645. Jerry Prince writes down an expression for what features of our scanner will change the spatial resolution of our picture. They'll make it blurrier or sharper, right? And he uses this very annoying Greek letter. I don't even know what letter that is. Somebody here does probably, but so we're just going to call that K, okay, because it's our spatial frequency number, okay? So this is our true object, the underlying true object that is providing the attenuation of the X-rays. This is our estimate of that true object, right? It's not going to be exactly the same because we have undersampling. We've got a whole bunch of things going on. And this is the arithmetic that gives us the convolution back projection, right? Now, we know we have measured this function here because this is the Fourier transforms of our GL thetas landing into Fourier space. So that's the data we have. Okay, so this is GK theta is our data that we have in hand right now. And then there are these other terms, detector blur, the windowing, the ramp comes, remember, from the Jacobian for this integration. And then the inverse Fourier transform phasor that we use to create, to map back from the Fourier transform we took. And we parameterize for any x and y. We have L, right, that is changing with respect to theta by this equation so that we stay on one line. So what are these terms here? So we know what this term is. It's a ramp that starts at k equals 0 at 0, and then it goes up just linearly, right? This is the window that we multiply that ramp by in order to make it behave better. And so we looked at a few of those. We looked at Hanning, Hamming, cosine, all of those things that roll down at high frequencies, we call the windowing function. So as more aggressively, if W goes to very low values as we move out in K, that smooths the image a lot because the high frequencies aren't admitted. And then S of K is the detector area blur, which basically is proportional to the width of our detector element, right? If we look back at data that we have, along here is L, and I sample that function with a separation that is given by the separation of my detector elements. So in a modern CT scanner, most of the time, those detector elements are 1 millimeter apart, okay? And sometimes they are 0.5 millimeters apart. And that's in an energy integrating detector like the Canon high resolution scanner has detectors that are 0.5 millimeters apart, which was a big leap in technology about 5-10 years ago. When you go to photon counting CT, it turns out you can make these detectors really close together, like 0.2 millimeters apart, right? So now you've got 5 times the sampling frequency that we had with an energy integrating detector 1 millimeter apart. Okay? So that's one of the big pushes to go to what's called photon counting CT, and we'll see that in a couple of projects, I'm sure. So that's detector blur. Let's go to the Ks. And so what else? Is there something else? We did mention it in the lecture, although it's kind of an advanced topic. It's hard to remember probably. There's something else that can blur our picture. Is there anything else? Pick anything. So one thing is, if you take the picture over time and the patient is alive, right, then they're going to move. So basically, the pulsatility of the vessels gives you motion during your acquisition. So that's going to blur the K-space data or your projection data. Even in your brain, your cerebral spinal fluid and the ventricles in your brain kind of move a little bit with your heart rate because you generate pressure in your carotids and it pressurizes your brain and then it drops and it pressurizes. So you actually get a little bit of motion up there. And then, of course, at the heart and other places like that, you've got lots of motion. So that's another blur. The other thing, and this is the advanced topic, is your choice of spot size when you're creating X-rays. So if we go all the way back to like our third lecture, remember we had basically a beam of electrons that came off a cathode and they hit the anode and we focused that beam down onto a rectangle. Ideally, we would focus them down to a single point, so all the X-rays emanated from the same mathematical point. However, that point would have infinite temperature, right? As you hit all these, electrons into that point, right? So you need a rectangle, and so the electrons hit that rectangle, and all the photons come out of that rectangle. That's going to cause blurring, right? And it's the best way of thinking about it, or the easiest way to think about it is, say I have a rectangle like that, and I divide that rectangle into a 2 by 2 array. So now I have a 2 by 2 array of smaller rectangles, right? I make an image from each one of those. Okay, so instead of making an image from the X-rays that come out of the big rectangle, I'm going to make 4 images, and they come out of the patches on my spot of X-rays. What is the relationship of those images? When you take the first one, right, and then you make an image with the patch next to it and take that image, it's actually shifted slightly. Those two images just shift slightly with respect to each other. And then what we do with the big patch is we just take all those X-rays, just add them up together. So we're adding up those shifted images, right? So in the end, it's basically like convolving your final image with that pattern that's generated from that patch. This really only matters when you're looking at super high resolution stuff. Okay, so if you're looking at a really tiny feature in the inner ear, like you can see all of the mechanics of the inner ear on CT, like the little, bones that have sort of what are they called? The stirrup and everything, these little things. And so when you're trying to image something that's down at that size, you want a really small spot size. When you're trying to image somebody for cancer in their liver, not as important, right? Okay, so we'll talk about the point spread function. So all of this stuff here goes into creating our point spread function for our image, right? So recall, this is review. We have an object in the scanner that's tiny. So what does that mean now? Now that you've thought about this a bit, tiny means when I project it, the signal from the shadow from that tiny object goes into one detector. It doesn't go across 2 detectors. It goes into one detector. That's a tiny thing, right? And then what's the image that comes out? The image that comes out is not a spike at 1 pixel, where it shouldn't be. It's a Gaussian, basically, a blurred thing. And the shape of that is given by these features. These are what determine that shape, right? As I set these things. So if my detector size, my windowing function sets what this thing looks like. And if the point spread function, and usually it is circularly symmetric, right? So it's pretty well, any way you look out, it looks the same. So you can just draw a profile through it and characterize it with this one-dimensional function, which is that profile. And so here's the point spread function with that profile drawn through. So this is space or millimeters this way. The modulation transfer function, remember, is the Fourier transform of this guy. It's over here in spatial frequency coordinates. Okay, so high spatial frequencies are in the creation of this point spread function because it's so narrow. As we go to a single spike, if my point spread function gets more narrow and more narrow and more narrow until it finally becomes a single spike, right? The Fourier transform of a single spike is, you got to memorize those Fourier transforms, the little pair. It's a flat line, right? So it's a constant. So the MTF looks like this. Everything's there, right? All of these high frequencies are equal if it's a spike. So that's why it's impossible to have a spike, because all these frequencies aren't actually there, because all of these things, right? This thing especially, it's going to get you, right? You've got a finite set of separations for your detectors. So then if we change from a Hamming to a Hanning, it might broaden the point spread function, and then high frequencies will be attenuated in the Fourier space, right? So remember, a ramp in the Fourier space looks like starts here and goes up like this, constant, right? And so that's what that K term is doing. The modulation transfer function, on the other hand, of the other features is going down like this. The total modulation transfer function that we see for a CT scan, like of noise or something like that, has 0 at the origin, right? Because whatever you do, you still have this term here. You need that term to do this integral properly. So this thing is 0 at k equals 0, right? So when you look at your Fourier space, once it's all said and done, it's going to start here, come up, meet this, and then go this way, right? We'll see that later. Just to review, recall, we asked, what does our imaging system do to a signal that has an amplitude and a frequency? It attenuates the contrast between the positive and negative pixels in this frequency, such that this pattern, once I've imaged it, looks like this. And then if as the frequency gets higher, it gets diminished by our system by this modulation transfer function, right? It goes down. And then the contrast between elements here drops so that we get much lower contrast, okay? So that's physically what's going on. So finally, it's just an average value, and you don't see that frequency anymore. That's when you're way out here at 0. So you can just measure the modulation transfer function on your system. And for CT, they can, the manufacturer will tell you, oh, our MTF hits 10% at, 4.3 cycles per millimeter. That's the resolution of our system, right, for this protocol. And you can take that home and say, okay, I'm going to compare these two scanners, which one's better? You get that 10% value and you compare it. And if it goes farther out, that scanner goes higher resolution, right? They don't usually give you the details of this whole function. They just give you that sort of where does it disappear number. Sometimes they say 1% here so they can make it a bigger number, right? So it's up to you actually to measure it, right? So you basically get this stuff and they say, oh, our scanner does this. And you say, thank you very much. And you take your phantom and you go to the scanner and you find out what it actually does, right? And so this phantom, these are probably pieces of aluminum embedded in perspex or plastic or something. And there's a distance. This is kind of like the hole phantom that we did a problem set with. As the holes got closer and closer together, right? You measure the contrast changing as they got closer and closer together. Same for this. As the frequency of these bars goes up and their gaps diminish, right? Eventually you say, this is the last set of bars that I can detect before I'm going to say that's no longer, I can tell you that that's bars of a certain frequency. And so that's my highest spatial frequency. And so this includes everything, right? So they can tell you whatever. You're now measuring it on their scanner. And this paper, you're welcome to go look it up. This research group claims that if they take the raw data and they pre-process it with their method, here they're going to generate higher contrast at that spatial frequency such that they can get to higher spatial frequencies, right, with their reconstruction technique. And to back up that claim, they just make the pictures. Say, look, here you go. So we do this a lot. So this is an interesting phantom. We're going to look at the effect of spot size with this, and also the effect of just resolution of a human-sized scanner versus what's actually there. So this is it's a human heart in a jar. In the jar is this stuff called formalin, which is a preservative. So you perfuse the heart with formalin, stick it in a jar, put a lid on the jar, and then you can just put it on the shelf and image it anytime you want, right? So we're taking it down off the shelf, put it in the scanner, and we take this picture. This is the ventricle with thrombin in it. And this is the right coronary artery. The bright stuff there, do I have a zoomed in? Yeah, I have a zoomed in view. But the bright stuff here is thrombin that's in the artery itself. This really bright thing is coronary calcium sitting embedded in the wall of the artery. This stuff is fat, has negative 90 Hounsfield units. And so we want to look at this feature. So here's the arterial wall, and this is on a Canon clinical scanner. I think it was a Canon. No, it might actually have been our scanner here. It might be the G. Anyway, so vessel wall, vessel essentially lumen is here with thrombin, calcium, right? This is that same object measured with the spot size increased by 50% on each dimension. So this picture was taken with a spot size of 0.7 by 0.9 millimeters, something like that on the target. And then this was done with 1.2 by 1.2, right? So you can see it kind of blurs. We'll zoom in, right? Here's the smaller spot size, and you get a central cross here, which is quite bright. Here, that kind of gets blurred out, and it's a lower amplitude. It mixes with the thrombin more. There are objects here that you've actually resolved that over here you don't resolve with this spot size. So this would be a high resolution object that you would hope that you could scan with a small spot size. The problem is if the patient is really big, getting the photons through the patient when you have the small spot size is a problem. That can be an actual issue, right? And this scanner that Canon made with the detectors that were 0.5 by 0.5, so 4 times as many detectors, they have an X-ray tube that has a small spot size, right, to match those detectors, right? Worked great in Japan because people are, thinner and smaller, and so you don't need as many photons. Germany, United States, Argentina, other places like that, you get these massive people, right, that you aren't going to scan them at that resolution. You just need to open up that spot size just to get the photons. So kind of a particular niche market. Well, Asia is a huge market, right? It's not niche. It's like, I don't know, 2 billion people. So to look at the ground truth as to what's there, I went to my friend's lab. And this is his setup, and we put the heart in a jar right here on this stand instead of this phantom. And he took a bazillion projections on this really high resolution thing. And we made these pictures of that heart in a jar on his scanner, and they're absolutely spectacular, right? This super high resolution. And we found the same vessel, and here it is. So this is the vessel wall. The contrast is a little different than on the human scanner because his X-ray energy that his tube makes is slightly different, and so it makes a slightly different looking picture. But here is that piece of calcium separated from basically the conduit, which is the arterial channel, and you can see that separation there. So comparing to what a human scanner gives you, right, to what is actually there, if you call this the ground truth, you see we still have a ways to go, right, to get to resolution that you would like to measure really fine structures on coronary arteries. When you go to measure a coronary artery on a real scanner, though, this thing isn't staying still, right? It's moving around, and so it's really hard. But with the advent of photon counting CT systems, which we now have one here, we got it like 2 months ago. You have the potential to make pictures like this. What do you think you have to do to make pictures like this that you don't actually want to do too much? We got to use more X-rays, right? Because it doesn't come for free. If you have a zillion more detectors, you need to put photons in those detectors. So if you just keep splitting the same photon flux, eventually each detector only has a couple of photons in it. So you need to up the number of photons to up the number of measurements in each of those small detectors. And that's a problem, right? We pretty well run out, but that's how this thing runs out. It's just like we can't use more photons because we don't want the dose to go up too high. So here's a phantom that is truly a tiny, tiny thing. This one's not a ball bearing. This is I think it's a 50 micron wire, right? And so you put the wire in the scanner and you just image perpendicular to the wire. So it's a really tiny thing, right? This is the image. We get our raw data, so we've got all our geothetas. And this is when we reconstruct it with this bone recon filter. We get this picture. When we reconstruct it with a standard recon filter, notice it's not called full width at half max, whatever. They just call it standard. There's no clue as to what the details are. Obviously, the background is much smoother, right? So all these details and the noise, they get smoothed down. We can do a plot through the signal that is generated by this wire. Remember, it's a 50 micron wire, so it's way smaller than the pixels that I'm showing here, which are probably, I don't know. So here, the dimensions of these pixels is probably like 200 microns or something, 0.2 millimeters or something like that. The point is, the object is a lot smaller than the pixels. So if I remember, this is standard on the left. This is bone or Romlock filter on the right. Here's a profile through that wire, and you can see it has a full width at half max. So you could model this as a Gaussian, right? Just put it in there as a Gaussian function and fit that thing and give it a full width at half max. The peak value it achieves is 500 Hounsfield units. Okay, for that voxel, so that's 500 Hounsfield units. And then the background this is true noise, right? It's just water at 0, right? So the Hounsfield units are 0, and the mean around 0 is here. So that's water with noise on it. Exactly the same data reconstructed with the Romlock filter looks like this. Now we get a narrower full width at half max. And the actual Hounsfield units at the peak is way up here, like 1200, whereas here it was 500. So it's much, much taller peak, right? It's a narrower, taller peak, right? And it kind of leads to the question, what is the correct Hounsfield unit for that thing, right? Well, for this thing, we know there really isn't we're never going to get down to the Hounsfield unit of tungsten, right? This is a tungsten wire because it's taking up only a small portion of the voxel. So you're averaging the background with the tiny tungsten thing, right? So it would go higher and higher and higher. If you get smaller and smaller and smaller, it would go to 5,000, 8,000, stuff like that. Okay. So a useful approximation when you're just back of an envelope saying like, what's my spatial resolution going to be? Whenever you have cascaded systems, if they're linear, right? So your signal goes into one part of the system and it blurs the signal, and then it goes into the next part of the system and that blurs the signal. You can calculate what the eventual total blurring will be, right, with a trivial formula, and it's not too bad. And that is for each part of the system that blurs it, you just take the full width at half max, square it, add them all up, take the square root, right? And that will weight them appropriately. So if my detector array gives me a full width at half max of 1 millimeter, so that's this part of the system, but my windowing, my Hamming function or whatever on the data, in addition to the detector array, gives me a full width at half max of 2 millimeters, then the combination of those two things gives me this, right? So it's mostly this, right? The 2 millimeters with a little additional stuff because this is here, right? So in looking at the signal to noise for these different reconstructions, different filters, we can go back to what we looked at before. Remember on the problem set, we were actually measuring signals to noise in CT. We have the mean of the background. We have the standard deviation of the pixel values in the background. We have the mean of our target, right, which is, say, a disk or something like that. And then the standard deviation around the inside the target. So if it's a disk, I can look at the standard deviation in the disk. Ideally, you would take a pixel and say, what's the mean of this pixel over 1,000 images? So just do the imaging 1,000 times and ask, for this pixel, how does its value oscillate or change randomly as I take more and more pictures, right? That's another way to generate this distribution here. For CT, because we're counting things, like we don't get negative values, we only get positive values, we count. It goes as a Poisson distribution. The actual distribution of values you see for a given mean number of events, right? As the number of events gets higher, as M gets up like at 50, 50 is really high, the Poisson distribution becomes a normal distribution. It's virtually identical, right, to the normal distribution. However, when you get down to mean values of 5 or 4, the Poisson distribution doesn't look like this, right? Because it can't go across 0, right? So it's kind of forced to have asymmetric shape. So that's what's used when you do simulations with CT. You have to, if you're simulating taking images down with few photons, like 5 photons in each detector, then you have to take into account that your noise variability will go with a Poisson distribution. And it's a big deal because what's the difference between log of 0 and log of 1, right? As those photons go down and you normalize with I naught and it gets closer to 0, the log function is firing away negative with a huge slope. So any change from 1 to 2 to 3 are huge changes, right? In the Hounsfield or in the GL theta data, right? So again, this is a review from what I did before, but if this is our target, say it was a brain tumor or a piece of liver tissue that we thought had metastatic disease in it, we want to make sure it's different than the background. You take the mean and the standard deviation inside the object. If you can achieve that, if it's uniform, you can say, what's the standard deviation inside the object? And then the mean and the standard deviation of the background, right? So here, these objects, it gives us the signal to noise, actually, of each of these. And 5, 10, 20. I don't believe that. Okay, CNRs in this figure. Okay, I believe this. I was going to say these CNRs are not 5, 10, 15, 20. Okay. So the CNRs of these disks here, just to give you an idea, the really good one is 1.7, 1.3, 1, and 0.39. So 0.39, you can't even see it. So the reason you can see those disks with such low signal to noise is when you squint, you integrate the pixel values inside this circle, right? And so your brain's pretty good at doing that, right? But that's sort of down in the very low end of the signal to noise. But for CT, you need to know how things behave at low signal to noise because that is often forced upon you because you can't use more photons. You've maxed out on your radiation to the patient. For example, say congenital surgery planning. Okay, so say a kid is born with tetralogy of Fallot or something like that, some congenital heart abnormality where basically everything is connected up in the wrong way, right? So a surgeon has to look at the heart and say, how am I going to plan this surgery to disconnect all of these things and reconnect them in the right way, right? So that's a big planning step for these surgeries, right? It's a tiny, tiny little heart. So ideally, you have a really nice rendering of that heart and its geometry so the surgeon can look at it, actually physically print it even, and take a look at how things are in 3D, right? However, you don't want to radiate kids at that age, right? Because the risk basically tracks with you over your whole life, right? And so when you're young, you don't really want radiation because it now you've got like a whole 100 years that could transform one of your cells, right? So whereas when you get to my age, I'm 65, right? So if I get in a car wreck and they don't know if I'm bleeding out, I was like, put me in a CT. I don't care how much radiation you use, right? Because the radiation ain't gonna kill me, right? At my age, that's not the thing that's gonna kill me, right? It's like also when you go fishing and people say, "Oh, there's mercury in those fish." So I don't care, right? That's not gonna kill me. That's right. Other things are gonna kill me other than the fish. Okay, so um, okay, so this derivation by Jerry Prince in the textbook, if you're a mathy kind of person and you really want to know like the underlying mathematical reason why the noise level of a CT image is what it is, right? Then this is the derivation for you. It's like 2 pages. It does take a while to get through because there's so many darn symbols flying around. But basically, if you have at a position in your image ij, you've got a mean number of photons detected there, divided by n naught, which is our basically our air scan, and that gives us this is what is GL theta, right? This is indexed as ij because the whole thing is done discretely, but it's GL theta here, and that's the average of GL theta. The variability or the variation on that goes as 1 over this, right? So as the mean goes down, the variation of this goes up, right? So the variance basically on your signal, which is GL theta, increases as 1 over the mean value of the photons in there. So as you use fewer photons, you get higher variance. Then he sets this up as a discrete problem where we have n is our number of views, and this I indicates which detector element we're on. So it goes from negative n over 2 to n over 2 detector elements. Those detector elements are separated by t. So most of the cases, this is 1 millimeter is our t. For the Toshiba scanner, or now it's a Canon scanner, t is half a millimeter, right? So they cut it in half, right? This is the ramp windowing here. This is our number of views. So like how many angles do we take? Do we take 100 angles, 200, 300, 400, 1,000 angles, right? And then the estimated value of our picture comes from this formula. And you can just translate this from the continuous case that we have. So he's basically comes out with this final result that the sigma value you're going to measure in the background, sigma squared, right, at a position, is proportional to 1 over m, where m is the number of views. So if I double my number of views, sigma squared goes down by half. Okay, so if I'm taking 360 views and I get a picture and I look at the noise in the background and I measure sigma and I get 1. So if I do basically 720 views and nothing else changes, the sigma goes down, right, by root 2. That's why you always talk about sigma squared, because you don't have the roots. Um, Also, sigma is going to go up as the mean number of photons that are used to make the picture in that pixel goes down. The sigma is going to go up as 1 over the mean, right? And interestingly, if you cut, so here we have n over t, right? So as I change my detector width, so if my detector width increases its width by a factor of 2, say I go from the Canon at 0.5 to the GE at 1, right? When I'm doing that increase, this thing goes up by a factor of 2, right? Because I got a bigger bucket, so I get more photons coming in that bucket, right? So interestingly, the signal to noise actually doesn't change as you change the ability to create a picture with that signal to noise doesn't change. So it says if I'm at a specific sampling rate and my signal to noise, right, doesn't look great, what I can do is just open up by a factor of 2, right? And then average all those together in there. And I will get a smoothed, it's a type of smoothing, lower noise image, right? The thing that's the killer, I know in this formula, is this one. And I'm sorry it's still got this crazy parameter for the width in K space, right? So this is like K max, right, is what this is. And it says, look, if you open up the window in K space such that your ramp goes up and it's of this width, but I say I double the width, I just keep going with that ramp, right? So double the width now in Fourier space that I'm going to admit for my reconstruction. Because that ramp is a 2D image and the ramp goes down to 0 and it's like this cone all the way around, as I open that thing up, the amount of noise power that I admit goes up very quickly, like with the third power of that width, right? So when we have this ramp function and we open up and we say, we want higher frequencies, I need to see smaller objects, I open it up, the noise jacks up by the cube of that width, right? So those are the interesting relationships between how you would design a scanner, right, and how you design your recon to get variance in the pixel values that you're comfortable with. Right? And one way of demonstrating this is with this thing called the contrast detail curve. And so we have three examples here, and the amount of noise increases as I go left to right. The percent contrast of each row, right, increases as I go from bottom to top. So remember, the percent contrast makes sense in CT. And then I add noise to my data and I redo the reconstruction and ask the question, how many of these circles now are outside my ability to perceive them, right? And two things are going to happen, right? You're going to have, it will move this way, so bigger circles with lower percent contrast will disappear. And these smaller circles, right, with higher percent contrast, but as the noise goes up, the small circles up here disappear. And so you get this kind of curve that contains those things that you can see and tells you the dimensions of things that you won't see in this picture, right? And it obviously depends on the contrast of the thing. If the contrast gets higher, right, eventually we can see something that's up here. But as we cross this line, we don't see this. And this isn't just a human. This is like if I know where that thing is, right? I know I come down here, I know there's a circle here, right? And I put a region of interest that's the diameter of that circle, and I put it on the image, and I do this experiment n times, and I get the computer to read out the signal there compared to the signal in the background, and tell the computer, okay, if it's higher than the background, call it positive, right? Say there's something there. It will just be random, right? Because it's gone, right? So basically the noise is too high to recover that mean. And this is where that, do you remember we talked about perhaps the Rose criterion? That is when you visually or on a computer, when you measure the contrast to noise from the signal to the background, that has to be 5 in order for you as a human observer to look at the picture and get it right like 97% of the time. Once it's at 5, you're kind of in the clear, right? If it's at 3, your performance is going to come down and you'll only get it right, say 80% of the time. Right? So that's called the Rose criterion. It's kind of an empirical thing. Okay. Maybe that's not true. Maybe it's actually because you could do it on a computer. You can test it yourself, right? Say I have a rectangle and I make the contrast noise of the rectangle in the background. I just keep dropping it. What's the performance curve as I drop the signal to noise? Right? It's going to be a continuous thing. So you just, I think, decide 98% is good for me, right? So that's called the Rose criteria, probably it. Okay. We have 20 more minutes. And nice. Okay. Again, all these nice books on this. So that's blurring we've looked at with those filters. Noise we've looked at. Artifacts. So not noise, but signal that's not supposed to be there. What does it look like in CT reconstruction? And now we go back to a question that was asked a long time ago in class. So it was, well, how many projections do you need to make a good picture? Right? So if I have a detector and it has 1,000 elements in it, right? And I have a field of view and I want to make an image of that field of view, and I know I have this 1,000 element detector, how many angles should I project? Take it, just, it's good, it's a good exercise just in your brain just to say, well, how many would I guess first? So I have 1,000 elements, here's my field of view, goes on to my detector, I have 1,000 elements. And now I have to decide, click, I'm going to get new data, click, I'm going to get new data. Like how many would it be to get a really nice picture in the middle there that's like 1K by 1K or something? Somebody make a guess. Yeah. Yes. That's a good guess. Right. It's not right, but it's a good guess. Right. So it's not going to be 50, right? It's not going to be 1,000,000. It's going to be related to your detector, right? Because when you click your detector, right, how far should you move? You should probably move like 1 detector element, right? Something like that. That's like, I don't want to move 50 detector elements, right? So, so it's about a K. We'll see it's actually pi over 2 times 1K. Okay. So there's a pi in there because it's a circle. Okay. Sorry to give away the answer, but it's a really neat argument as to why you need that many. So here we have our geometry. This is what we're using here. And we're gonna click, this whole thing is gonna click this way when I do my theta, right? It's gonna boop, move that way. And then we'll get our next set of measurements. Let me put this on here. So there is a toy problem of MATLAB that's on the site that you can, I think you already did play with. Maybe it has like point elements, like just pixels in there that you can throw up and make a sinogram with that and look at the results. add noise to a sinogram, look at those results. And you can use it to get an idea of how the images basically fall short when you don't have enough projections. So you can just use the simulation and say, well, I'm going to do a 256 squared image. Let me do 45 views that are sampling 180 degrees, but it's just 45 of them, right? And the picture, the noiseless picture comes out like this. If you add noise to the raw data, it comes out like this. And you can see in both cases, it's fairly obvious that you're undersampled in theta because there's these artifacts in the picture, right? This is not part of the object, right? All of these things flying out here. So you have this very complex pattern of interfering streaks that are going out into space. And that's what undersampling looks like when you undersample in theta. The noise kind of mixes it up a little bit, but it's the same basic thing. If we go to 90 views, so now I'm going to double the number of projections to make a picture. And remember, these projections now, they're still going from, say, 0 to 180. They're just taking smaller steps to get there, okay? So we haven't missed any big swath of projections in doing this. 45, it goes 0 to 180, but in big steps, like 4-degree steps, right? And then here, we're going to go do the same thing, but we'll take twice as many by taking the step in delta theta to 2. And so it changes the picture. I'll flick back and forth. So this is 45 views. If we look over here, that's 90 views. So you can see the sort of frequency of these streaks doubles. We just lose all the streaks here. And this picture looks pretty normal in the middle, but it still has kind of streaky business out here. That's 180 views. Now virtually everything's gone in terms of artifacts, right? Because these are 1 degree. And 360 views. So between those two, we are losing some artifacts, specifically way out here, right? But principally what's happening is that 1 over m, term in that signal to noise or the variance, the 1 over m is kicking in so that from 180, I get a picture. It has a certain background variance here. Looks kind of hashy. If I do 360, I don't really change the picture, but the noise goes down. So, and then 720, same deal. The noise just keeps getting better. So the interesting thing is that if you ask, in this field of view, so I took 180 views, so 1 degrees, right? This is a 256 squared image, so each pixel is 256 by 256. When you look at the artifact out at the periphery, it's obvious that there's artifact, right? It's just kind of like a correlation of the signal going radially out from the center here, so that's a weird looking picture. But there's a field of view within which it just looks kind of like a signal with noise around it. There's not a lot of artifact there. And so this is an indication that perhaps there is a region within which this image is sampled well enough in terms of theta, just taking 180. And it kind of makes sense, right? That as you go towards the center, 180 samples, right? Because we're towards the center of K-space, when we're clicking those things around, we're sampling at a pretty high rate, right? And so perhaps it's enough in this. So is there a magic formula to give us, a diameter here that is okay? Inside that diameter, things are okay with 180 views, right? That's another way of asking the question, how many views do I need to make a decent picture if I've got a certain number of detector elements? So that artifact that we saw, this correlation out here and the streaking and stuff is called view aliasing. And as you project things back, you can see that towards the center of the image, we've got a lot of data projecting one on top of the other. So we have a pretty high sampling rate at this center part, but out here, our sampling is suffering, right? And this is a really early CT imaging book from the 70s, actually, by Cack and Slaney. And what it's showing is number of projections this way. This is just an ellipse, this thing here. Here's the number of projections. And this is the samples per projection, or basically how many samples along L do we have? So this is 512 samples along L with 512 projections. So that's the first guess that we made, right? Was, let's say if I have 1,000, we'll say we need 1,000 projections. And you can see, yep, it looks pretty good all around here. There is a bit of stuff outside a certain radius that looks like it might be artifact. As I take fewer and fewer projections, I start getting these very complex overlapping signals that tell me I'm not sampled well enough. And so this is view aliasing, it's called. It looks pretty spectacular when you have a lot of detector elements, right? And not enough angles, right? If I have 64 detector elements and 64 angles, I get something that does have obvious artifact out here, but not as spectacular as that. So it takes us back to our, I think this is the second lecture, maybe third lecture, where we had a signal and it had 1 cycle per millimeter. So this is 0 to 5 millimeters, 5 cycles, 1 cycle per millimeter. And the sampling of that signal was every 1/10 of a millimeter. So I have a beautifully rendered sine wave. And as I drop my sampling rate, we found that the rate that is required to reproduce this signal well, right, was called the Nyquist criterion. And I needed basically 2 samples per wavelength, 1 up, 1 down, 1 up, 1 down. So whatever that period was, I needed 2 samples per that period to hit the Nyquist criterion, such that I could achieve rendering this sine wave without bleeding in energy from, higher frequencies, etc. Okay. So let's go back to this example. Here's a diameter, and we can ask, inside this diameter, perhaps I am achieving the Nyquist criterion in both the L direction and the theta direction, right? And so it turns out that to match the Nyquist sampling in both L and theta for 180 views here, I basically need, it gives me a width of 115 pixels across here, and we'll see how we can derive this relationship. So inside this orange circle, our theta sampling of 180 projections is enough. Outside this circle, it's not enough. And inside this circle, we have achieved the Nyquist criteria in our sampling of the 2D function. Outside the circle, we have not achieved that. Okay, and that's why it looks artifacted. What are we at? 11, 9 minutes. Okay, so aliasing artifacts take on a couple of appearances that we've already seen here. So here's our perfect object with no aliasing. Insufficient number of detectors, so I can't really resolve these edges particularly well, right? And because of that, as I'm moving by, that I can jitter which detectors see the edge, and I get these streaks coming out from the edges themselves. And then if I take an insufficient number of views, but I have a lot of detector elements, then I get these artifacts out in the field of parts of the field of view where the delta theta is not sampling well enough. So we can do it actually mathematically and figure out what our diameter is or how many views are required to achieve a good sampling. So here's GL theta. This looks like the Fourier space that we've been mapping out. It is not the Fourier space. This is GL theta. I'm in X and Y. Okay. I don't know why X is up there, but anyway. And my sampling is along this direction, and I have a delta L distance between each sample point. So for a standard old scanner, this would be delta L would be 1 millimeter. I would get a sample every 1 millimeter at a theta of 0 degrees or a projection in the vertical direction. Then I click my theta to a new projection, and I take those same delta L projection data here. Okay. In Fourier space, because of the projection slice theorem, we know that we're sampling the Fourier space in the same line as this one, right? So here's Q, Kx, Ky, and this should actually be Y. Sorry about that. I have samples across here and Kx, samples across here at this angle. Okay. So the question is, if these sample points here are delta L, ideally, what should the sampling distance be between, say, this point and this point be to match this sampling rate? So I'm sampling at 1 sample per millimeter this way. If I ask the question, which is the thing I can change with delta theta and how many projections I take, it's like, how many samples do I get as I'm changing delta theta? And what is the distance here? Is this sampling rate, so let's take this example, but this one's easier. Here's 1 millimeter. When I step up to here, how far is that? So if this is 1, this is like bigger than 1. It's like 2 or something, right? So when I go along this trajectory and ask, what is my sampling rate in the theta direction, right? Then I get a much lower sampling rate out here. It's like 1/2 of the sampling rate in the radial direction. Okay. So basically the field of view that is sampled well and matched between this direction and the theta direction is when I look at 2 points here, they're this 1 millimeter and this 1 millimeter match, right? And that's when I've hit the Nyquist criterion for theta, and that will keep me inside a field of view here, right? So it's interesting in CT, right? If you put something at the origin or an object close to the center, right, you really oversample that object in the theta direction. You get a ton of views of that thing with very little change, right? And so the image quality at that location will be better, right? You've just sampled it more, right? And so way out here, I'm not sampling in that theta direction very well, right? So my angular change of my projection for that object that's out here will give me a much different signal. So it's an undersampling basically in that direction. So you can just write down the arithmetic, and it's pretty trivial, right? We've got delta L is our distance between sample points, and the number of points we have in the projection direction is n, this thing. So this here is the field of view, okay? That's the field. We're going to define that the field of view. Okay, here's my detector array. I've got my field of view, okay? I know that my number of views as I go around here times delta S, which is this distance. Boom, here's delta S, and I take my number of views. So I measure that arc. How long is that arc? Right? Just in millimeters. I know it follows this, right? It's, pi d, right? Divided by 2. And so here it is, pi d divided by 2. And it equals the number of views times delta S, right? So that's our relationship between the field of view, delta S, and our number of views that we're going to take, okay? So if I ask the question, I make this assumption. I say, let's set delta S equal to delta L. So I'm just going to go find the place where delta S equals delta L and find out what field of view that is. And it says n views, right, is pi over 2 times the number of projections, right? To basically give me that relationship that delta S and delta L are equal, right? That's the number of views that I must take in order to make that relationship work. And so that is the Nyquist criterion for sampling in theta, right?
Wait, sorry, could you repeat? Oh, no.
Say that again.
Can you repeat how you got that second equation, the pi FOV over 2?
This guy here.
Mm-hmm.
Okay, sure. So the arc length as I go along here, right, is basically equal to the number of views, because here's 1, 2, 3 views, right? So I just multiply delta S times the number of views. That's an estimate of the arc length, right? I also know that that arc length is pi times the diameter of the circle, right? Divided by 2, right? Because it's 1/2 of the whole circumference. Okay. So that's just geometry, this guy. And you have to believe that I can just multiply n view of these together to get the arc length. But that's pretty good.
Gotcha. Thank you.
Okay. Good. So it's related, the number of views that are required to achieve this, right? A circle that has this is related to the number of points, right, on the projection. And it's pi over 2 times that number of points. So your guess of 1,000 was pretty good, right? It's right on the money from an order of magnitude sense, right? But it's pi over 2 times that. So it's like 1.5 times that. Okay. Okay, I think we're done. That's 20. So